Hello everyone. This is Thomas Sir. I'm the EVP of the Kitalys Institute, the organizer of today's webinar, Knowledge is Power, Realizing Disease Prevention and Individualized Disease Management. Our featured speaker today is Stanford's Professor Michael Snyder. He's the chair of the Stanford Genetics Department. He's a world leader in multiomics, wearables, and a number of other matters. A couple housekeeping points before we begin. First, please keep your mics or phones on mute. Second, please type any questions you may have in the chat box, and we'll get Mike to try to answer as many of those as we have time for. Just to warm the chat box up, those of you who are willing, please introduce yourself in the chat box and indicate where you are logging in from. 3, we are recording this webinar. A YouTube video of the full webinar and PDF version of the slides will be posted to our Kitalys website within a couple business days. Registrants will receive links by email when these materials are available. Just a word on the Kitalys Institute. We're a not-for-profit 501c3 tax-exempt institution dedicated to the acceleration of the translation of the biology of aging into public health, the prevention of chronic diseases, and the extension of healthy longevity for all. We organize the annual Targeting Meta-Obesity Conference, the 5th edition of which will take place on October 10 to 12, 2022 in Washington, D.C. and virtually. If you enjoy webinars like today's, please visit kitalys.org for more information. And I now turn the mic over to Kitalys Institute founder and president, Dr. Alexander Zan Fleming, to introduce Dr. Snyder. Zan?
Well, thanks, Thomas, and good morning, friends and colleagues from around the world. It's great to see the diversity of this audience in geography and many other ways. We have today a landmark webinar, which in every way reflects what the Kitalys Institute is about, targeting with cutting-edge science and technology, the biology of aging and root causes of chronic diseases. And in doing so, to produce practical, valuable solutions as soon as possible. We do that by breaking down the silos that separate the collaboration of key stakeholders. As this audience reflects, we break down not just scientific and therapeutic silos, but clinical practice, regulatory, public health, policy making, investors, commercial folks, and other silos that don't communicate and collaborate as well as they should. Now, by signing up for this call, you know by now that Michael Snyder's exceptional credentials and productivity are just over the top. I'll just say that Mike has built at Stanford probably the most productive, the most robust precision health ecosystem in the world. He and his over 100 colleagues turn out game-changing scientific discoveries on a regular basis. But just as importantly, Mike and colleagues are showing us what we can do now and not wait for decades that it may take to have robust pills and injections to modify the aging process. He's showing us how to maintain health and to control the aging process and to avert the onset of chronic disease. They at Stanford are making good on their stated mission to fix the broken healthcare system and create equitable solutions for care. By the way, I don't think we have a healthcare system. We have a disease management system, and it is broken. So Mike, I could go on, but let's go right to you, and we'll be back with the audience to chat when you're done.
All right, well, thanks so much for that kind introduction and having me here. It really is a delight to be able to speak to all of you. I was just looking at where folks are from, and it really is from all around the country and all around the world, which is pretty cool. So our shtick, if you will, is actually to use big data to transform healthcare. And I will touch on all these topics that are in the title. And I don't mind being interrupted if anyone has any questions. So I'll start with the premise that Zan just mentioned, which is our healthcare system is broken in many, many different ways. I'm sure all of you have experienced this. And the one he focused on is one that certainly troubles me a lot, which is that it really is focused on treating people when they're ill rather than when keeping people healthy. And as such, it's very reactive. We normally measure very few things when people are ill. When you're healthy, you're rarely measured at all. And I would argue some of the things you get measured for are of questionable value. But here's one of the biggest problems, which is nearly every decision about your health is based on population-based measurements. Instead, I think we would all agree we should be focused on keeping people healthy, as such, be very proactive. We're certainly capable of measuring many, many more things. The frequency, I would argue, should depend on what you're at risk for and what your trajectories look like. That should determine how often and what kinds of measurements you might take. And lastly, I think we'd all agree we should be doing individual-based medicine rather than population-based medicine. And many physicians say we do that already, but I would argue not at the level we should. And we should be very focused then on precision health rather than precision medicine. And this is actually a big theme of the Stanford Medical School. So just to illustrate this point, you've been taught since you were little that your oral temperature when you put a thermometer in your mouth is 98.6. And it turns out that number is wrong. If you actually look at a population study like this one here is pretty representative, the number is more like 97.5. But the more important point is that there's actually a spread. Some people have their baseline temperature is 94.6 and others 99.1. There's 25th quartile at 75th. And what that means in today's world, if this is your normal baseline temperature, when you go to a physician's office and if they put a thermometer in your mouth and measure at 98.6, you'll be up 4 degrees over your baseline and they'll tell you you're healthy. Everything's fine. What are you doing here? Go home. But the reality is, of course, you are probably quite ill. And so that's a theme I'll hit on many times. It's really, really important to understand your baseline so you can detect when you're getting disease at a personal level. So many, many things impact your health. Obviously, your genome, your DNA, but many other aspects as well. Environmental exposures, and today, pathogens certainly like COVID are very dominant in our thinking. But other factors such as stress, food, exercise, all these lifestyle factors we know impact your health as well. And we're in a world where it's now possible to quantify a lot of this. In fact, our lab's spending a lot of time on this. Some of it you can do pretty well, your activity with these wearables. We can certainly sequence people's genome. These others are a bit clunky. Food is not that easy. You can capture the information. It's not super easy. And these are areas we're working very, very actively on. I probably won't have time to talk about today, but we're actually working hard on environmental sensing. So a number of years ago, just to try and see if we could get at this concept. So obviously these things impact your health, and we can measure them beyond just these sorts of things. You can measure their impact on your health by doing deep biochemical profiling. So a number of years ago, we set up something we call Personalomics Profiling, where the idea is to use these advanced technologies like genome sequencing, other technologies, some of which our lab has invented, for looking very, very deeply at people's molecular profiles. And so we'll follow their epigenome. For those who follow this sort of thing, this is their DNA methylation, transcriptome. These are done off your immune cells called peripheral blood monocyte cells. We'll also look at proteomes, cytokines. These are important immune molecules, metabolites, lipids. These will profile out of your plasma, so the fluid in your blood. We also follow people's microbiome, meaning their gut and nasal initially. Now we have tongue and skin data. It's really quite fascinating. And we'll follow this as well. We do deep clinical testing, questionnaires, some advanced tests like stress echocardiograms, glucose control measurements. You'll see that later. And about 8 years ago, we brought on biosensors, wearables specifically, to try and follow people's physiology continuously. And I'll talk about that quite a bit at the end. So one aspect is to collect deep data on people. We started this on me, extended it to 109 people. And we've been running the study now almost 9 years come March. And so one aspect is, say, is deep data. The other aspect is longitudinal. We're sampling people over time while they're healthy, every 3 months typically. And if an adverse event comes along, like a viral infection, we'll take many more samples, typically 5 to 7 additional samplings. And we'll also collect other times as well, other health events or maybe interesting trips people take. So you might say, well, why are we doing all this? Well, we're trying to understand what it means to be healthy. How does that change over time? That's going to get us into talking about longevity. How does it differ between different people? What happens when you first get ill? What goes on biochemically with you? And perhaps most importantly, can these advanced technologies that measure all these things, can they be valuable for actually managing people's health? And with regard to the last point, one thing we found is that even though this is a small group of people, 109 people, we had 49 major health discoveries just in the first 3.5 years. And they spanned a wide range of different areas. So hem-oncology, cardiovascular disease, metabolic disease, so on and so forth. We discovered, and in all these cases, it was pre-symptomatically. We found these things. So as an example, we found someone with early lymphoma that was picked up by imaging, 2 people with some pre-cancers. They can convert to aggressive cancers, 2 people with serious heart issues, one through genomics, another through wearables, diabetes, I'll talk about a little bit, so on and so forth. So the point is we actually found a large number of things, and no one technology did it. Sometimes it was genome sequencing, sometimes it was imaging, often it was the deep biochemical profiling would uncover these issues once again before people are symptomatic. And just to show you a few examples of this, genome sequencing was quite powerful for the first 70 people. We've extended this now, but 12 of the first 70 learned something very, very important from their genome. And these are what you call Mendelian diseases for those who follow this sort of thing. So these are cases where a single gene variant can cause illness. So the most famous is probably that many of you are familiar with. It's called BRCA. People with BRCA mutations are at high risk for breast and women ovarian cancer. And so we actually had an individual who had this, who had no idea. 3 people learned something that turned out to be pretty darn important. So this person had a mutation in a cardiomyopathy gene, and it turns out has an underlying heart defect, was fairly young, had no idea, but his father did die in his 60s of a heart attack, and his aunt had one in her 50s. So he undoubtedly then had the same problem, and this is likely the culprit. There's another individual, and he's now on medication as a consequence of this. He actually did a stress echo, and it turns out he does have a heart defect. There's another individual had a mutation here, 2X means over 2. Had a mutation here, also fairly young. They did a whole body MRI follow-up, and sure enough, turns out they had an early thyroid cancer, and that was removed, and they were able to keep most of their thyroid, so that was good. Coming into the study, 9 individuals were thought to be diabetic, by type 2 diabetic, but one of them turns out to really have a mutation here, HNF1 alpha gene, and they're a different kind of diabetic. They're not really type 2. There's something called a MODY, and there's actually a better medication for controlling a MODY person than a type 2, so they actually switch their medication, and so on and so forth. So we think genome sequencing can be pretty powerful. Now, obviously, not all the 70 people learned something important, but for these 12, it was a pretty big deal. There's a 13th that learned something important about their drug sensitivity based on the drug they were on. So anyway, a lot learns things about their genome. Now, one problem with this kind of analysis is getting in for the aficionados, but these are these mutations that can cause disease, but most common diseases are actually not thought to be due to single mutations. They're thought to be due to combinations of our changes in our genome, and you add them up and they can actually lead to a significant risk for disease. And the most famous is probably type 2 diabetes, but coronary artery disease, AFib, all these diseases I've listed here, there are single gene changes that can lead to them, but more often than not, it's thought to be due, as I say, to these variants. And so the way people are analyzing genomes these days for this sort of thing is they'll sum up all your variants, both your protective ones as well as your risk variants, and try and generate what they call polygenic risk score, and try to determine from these variants whether you're at high risk or low risk. And it sort of works, actually. It can, these days, you'll sum over literally millions of thousands to millions of these variants. And then you can make predictions about people's risk. And it kind of works for the top couple percent if you're really at the extreme end. And it worked for me. It turns out I'm type 2 diabetic. And it's because I'm very, very high on this polygenic risk score. So, but there's some problems with the way this analysis is done. One is that it assumes that genetics is linear, and we know it's not. And the second is that it ignores all the rare alleles, which could also contribute, so the rare variants. And so we've come up with new ways of analyzing genomes. Again, this might be more for the aficionado, but we can actually start dissecting some of these complex diseases. And we started with one called abdominal aortic aneurysm. It hits about 10% of people who are 60 or older. And it's not the highest causing cause of death, but it's, it's reasonably high up there. And one of the reasons we're very interested in that, it's known to be genetically heritable, but nobody's really solved the genes underlying it. And the way it usually gets diagnosed is what's shown down here is their aorta basically grows and then bursts, and then of course they die. So that's a terrible way to diagnose a disease. So we wanted to see if we could come up with new genetic methods for trying to be able to find genetic risk for this disease. And we came up with a whole new way where using whole genome sequencing. So by sequencing just a reasonably limited number of cases, 268 cases, 133 controls, we could use machine learning actually to be able to find all the genes that are enriched in cases relative to controls. We also bring in some electronic health record information as well. And it turns out it worked pretty well. We identified 60 genes involved in this disease that actually we think contribute quite a bit to it. And so, we went on to characterize these genes. They're exactly the sort of thing you would expect. They're involved in blood circulation, blood pressure, aneurysm, and so forth. So they're mouse models of these diseases cause aneurysm types of defects and also are misexpressed. So are the human genes misexpressed in AA patients. And then we went on to actually set up a risk score. In this case, it's a bit polygenic, but it's based on our 60 genes, and actually works pretty decently. So you can make predictions of people's risks just from a genome sequence. And if you add a little bit of electronic health information, it's not too bad, 0.8 risk prediction. So for the first time, we think we can make predictions about who will get this based on a genome sequence and a limited number of health information. And we've gone on now to extend this study. I don't think I put the slides. No, I guess I have one. We've actually used this for looking a different version of this for looking at ALS. That paper just came out. There were 15 genes known. We found 690 genes involved in ALS. It's really this approach, this machine learning approach is really going to be revolutionary for analyzing genomes. And then more recently, we've applied it to COVID-19 severity. So obviously, if you're very, very old, you're at high risk for COVID severity, meaning you'll get hospitalized and possibly die. But it turns out that a lot of young people, right, wind up in the hospital and die, and it's not clear what's going on with them. And it's known that there is some genetic susceptibility. So we wound up using our machine learning approaches both for common variants and rare variants. I won't have time to go through all this, but we basically, with this approach, we found 1,375 genes involved in COVID severity. And for this one, I think it's about 800 genes. And so this approach we think is going to be super, super powerful for being able to analyze genomes and make predictions about people's disease risk. So I'm hopeful that in the future, we can better be able to, when we sequence people's genomes, be able to make predictions about their disease risk. So genomics, as I say, is just one aspect of all this. We think other technologies are very powerful. For the case where we discovered the lymphoma, it turns out it was imaging plus a few biomarkers, and that's a common theme too. Usually multiple kinds of measurements are very, very powerful for detecting when things are going off. So this person had a large spleen and actually got treated and is in good shape, actually. And again, all pre-symptomatically. Here's an individual, also pretty young. Turns out they had, from their biochemical measurements, way too much, it's called IgM. It's a type of antibody compared to everyone else. Their two samples were just way, way higher than the other 998, 1,000 samples here. This person's were higher, and the follow-up revealed that they had this pre-cancer that can convert to aggressive cancer. So it's kind of actually useful to find this. I have my own theory about what this person should do. I should point out, I'm not an MD, so you don't have to, you don't have to trust anything I say, but I think that's a plus. I think medicine is best executed by the people themselves. 6 people had plaques in their arteries. I'm one of the 6. I had small amounts of plaque, kind of like this is not me, and the recommendation here is you increase your statins, which is done for me, and it seems to be going away by actually doing this. So we think that's positive. I mentioned before that coming into the study, 9 individuals thought they were diabetic, were in fact diagnosed as diabetic, and a few knew they were pre-diabetic. But it turns out when we first enrolled them, it was pretty clear there were 2 additional people who were diabetic and many, many others who were pre-diabetic. And this is pretty common. 9 out of 10 pre-diabetics have no idea. So I'm pretty sure a lot of you listening to this webinar are probably pre-diabetic and have no idea as well. And we think this is a big deal. And I'll spend more time on this a little later when we get to the wearables. Now, one of the things we really wanted to know is how do people become type 2 diabetic or diabetic in general? I mean, do they just gradually get there? Does something trigger it? What's going on? So by profiling people over time, we could actually see what was going on. And it turns out that during the course of the first 4 years, 9 additional people became diabetic and others had diabetic range values. A number of other people became pre-diabetic. I hope you can hear me. It just said my internet's unstable. So I trust you'll break in if you can't hear. Just send a chat or something. I'll keep the chat window open. Okay, so all right. So anyway, as I say, and then others had diabetic range values. They weren't necessarily classified as diabetic, and of course others became pre-diabetic. So the question is just how do people become diabetic? Well, the answer is of the 9 who were clinically diagnosed as diabetic during the course of the study, 2 gained weight, which is sort of the classical way. Their microbiome diversity dropped and their glucose was out of control. But the other 7 didn't gain weight. 5 of the 7 just gradually became diabetic. Like there's 2 down here, 2 examples here. So orange is fasting glucose. This gray is hemoglobin A1C, a marker for diabetes. And basically, these 2 individuals just gradually became diabetic. This one, I believe, went on metformin, and this person gradually became diabetic, first classified by oral glucose tolerance test, different kind of test. So they gradually got there. But 2 other people, it seems, got triggered. And I'm one of the 2. This is me. This is 8 years of data for me. I now have, believe it or not, 11, actually almost 12 years of data. So yeah, and for me, I first became diabetic after a nasty viral infection. You can see I was pretty normal. And then I went in because my genetic test said I'm at high risk. And I went in for a glucose insulin resistance test, and they measured my fasting glucose, came out high. And then later I got measured again, and sure enough, about a week later, I basically was classified as type 2 diabetic because I was 6.7 hemoglobin A1C, which is 6.5 is the number for diabetes. So it's arbitrary, but that's the number they use. And same with my fasting glucose, so it's definitely over the limit. And so I know this doesn't look like much, but I actually did a pretty serious intervention. This is about 10 months of data, where I basically cut out all sugars, which I almost never have. And I had been biking, but I doubled my biking and started running, and I gradually brought it down to normal. And so in my case, it's pretty clear that I'm genetically predisposed, and then something triggered it. We think it was a viral infection because I had a nasty viral infection right here just at the time. And it turns out, I won't share the data, but my DNA methylation, my epigenetics changed during this time. It's kind of interesting. And then it went back to normal later. It was actually running boringly low, and I stopped looking at my data. I was still collecting it, but stopped looking at it. And someone else looked at it here and said, Mike, you realize your hemoglobin A1C is back to 7.0 at the time. So gosh, I have no idea. Looked back and saw when it went up again, and sure enough, it happened when, guess what? I stopped running here. I also had a nasty viral infection, so it's probably one or a combination of both. And so I was reclassified as diabetic. And basically I started running again, and I got it down, never down to the baseline levels of before. And yeah, and that seemed to help somewhat, but gradually it kept creeping up over time. So I started becoming gradually more and more glucose dysregulated. And finally, I was running about as much as I could, about 4 times a week, 4 to 5 miles a run, 45 minutes. And basically, it still kept creeping up. So I switched from running to weightlifting about 5.5 years ago. And the logic is that muscle mass is better for glucose homeostasis. And it turns out that failed miserably too. I kept creeping up. So finally I bit the bullet and I did what a lot of people said I should have done in the first place. I took metformin, frontline drug for type 2 diabetes. And guess what? I'm a non-responder. And so in fact, I kept creeping up. I'm going to hide the picture. But basically I went all the way to 7.5 I was not responding at all. So what I did was basically got more data. If can't figure it out, the answer is get more data. And the answer was I'm insulin sensitive and I make insulin just fine. So my cells are responding, so I make insulin. So what's the matter with me? Well, I don't release it from my pancreas. And you can measure this in a couple of ways. One is glucose disposition. Turns out I'm very, very slow in getting rid of my glucose because I'm not releasing insulin from my pancreas. And there's a drug called rapinolide that actually promotes that. And turns out I'm a good responder to that. I'm now on SGLT2 inhibitors, which also have certain benefits. So, and that I respond pretty well to those. So the key was to get more data. We call this precision diabetes. By better knowing what was wrong with me, I could better manage my glucose. And I think this could be done for everyone. These are not expensive or hard tests to run. So anyway, yeah, we think this is super important because it will help manage people if we can better understand. I think diabetes is 50 disease. I see something in the chat about how there's a big burst in diabetes after SARS, after SARS-2, after people are getting COVID, about 4% go on to develop diabetes. And we think it's very parallel to what's going on with us. I think it may be due to epigenetic changes. Certainly it's inducing things. So this is why we think it is important to know these things. Now, one of the most important things we learn from all this deep profiling, you'll like this from the longevity standpoint, but one of the most important things we learned is that people's profiles, they're actually quite personal and they're quite stable. And so I'm just showing this for 12 people with 10 or more healthy visits. And it doesn't matter which ohm you look at, your metabolites, transcripts, meaning RNA, clinical lab cytokines. Every dot's a different visit. Every color is a different person. For me, there's 6 years of data. I'm the light blue. And you'll see that all my dots cluster together. I mean, they're most similar. And the brown person, the red clusters together, the red, the yellow, so on and so forth. So the point out of all this is that we have these personal profiles. And in my case, it's 6 years of data and they still cluster together. They're pretty stable. And not only that, if you undergo a perturbation like a viral infection, some people do weight gains, weight loss, or exercise, you will shift your profile. This is after acute bout of exercise, right? People running to their VO2 max. Half your molecules will change, but you will still look more like you than anyone else. So this is an exercise study where we profile people through the exercise bout and recovery, and all their time points cluster together. You'll see each color is a different person. I actually did it twice, and my 2 dots cluster together, even though they're a year apart. So again, we think these are pretty robust, pretty stable profiles. It has interesting privacy implications. But the reason this is a big deal is that what it's saying is that the difference between people is greater than the difference between, say, a viral infection or not, or exercise versus not. And so this is why we argue it's so important for personalized medicine to know your baseline, because it's very, very easy to tell when you're getting ill because you'll shift your profile compared to you. But it's very, very hard to tell when you're trying to compare a sick you with 500 other healthy people, because again, the difference between people's a lot. And this is why these GWAS people need thousands and thousands of people in their study, because the differences between people are greater than the difference between a disease illness and a healthy baseline. And so this is, again, I would argue you should be getting your healthy baseline now while you're healthy, not later. Now, I told you that most molecules are pretty stable and don't change, but there are some that do. So out of the 20,000 molecules and many zillions of microbes we're studying, it turns out that a subset of them will change, and they change it 2 times. One is seasonal and the other is actually through aging. So we're going to talk about each of these. I think they're quite fascinating. So we asked a pretty naive question. If you think about it, you've been once again told since you were little that there are 4 seasons and they're 3 months each. And if you think about it, who says why are there 4 seasons? Maybe there's 2, maybe there's 15, I don't know. And why would they be 3 months each? It doesn't even make any sense. Maybe some are 2 weeks, maybe some are 4 months, 6 months, who knows? So we let the data tell us how many biological seasons there are. We basically say, let's look at all the molecules and microbes they're following, how many of them show seasonal patterns, because we have 1,000 samplings total throughout the year from these different people. And it turns out there's 1,192 molecules and microbes that show seasonal patterns. And these are just some examples here. Many of them are known, very few at the level we've mapped them out. But yeah, there's a lot of known ones, and then a lot of new ones we discovered as well, new molecules. And so you can see these seasonal patterns throughout the year. A1C peaks here around April, May. Okay, so then you can say, well, all right, we have all these seasonal molecules. How many patterns do they fall into? Is it 2? Is it 20? What is it? And the answer is it's 2. So there's a mathematical way of showing it. It's called an elbow plot. We can show that there's 2 major seasons, obviously smaller ones as well. And you'd say, well, that makes sense. The people are profiling, they're in the Bay Area, they're Northern California. Makes sense. One should be winter, one should be summer. And you would be half right. So a lot of the molecules do peak in winter. There are things involved in your infection responses and things like that. Even acne, that's actually known already. These things are known to peak in winter. But the other set is not summer. It's actually late spring, early summer. It's April, May. And in hindsight, it makes a lot of sense because allergy and asthma are some of the molecules that are peaking here. But it turns out also cardiovascular disease, metabolic disease, type 2 diabetes molecules are peaking around this time too. And our explanation for this is that even in California, people don't exercise as much in the winter. It is cold for us here, our highs have been in the low 60s, even in the 50s this year. It's a little strange, but, and, it rains. And so people we think don't get quite as much exercise in the winter, and then spring comes to exercise. And so they improve a lot of these markers. And so that's our explanation for this. There's some other things, seizures and sleep also, molecules associated with that seem to peak here. I don't have a full explanation for that. So there's plenty more to learn out of these data. What's kind of powerful about this, though, is that a lot of these molecules actually are clinically important. So many of them will show the peak at this time or in the winter. And so we think, once again, it's pretty important to know this information. So first of all, if you're too far out of range, you might want to get a boost. Knowing that you may be going low in the winter might give you some boost to actually start improving, your cardiovascular things and eating habits, so you don't spike too far. And the other is maybe if you're here, it's late spring, you realize you'll probably come out of it if you do what you're supposed to do. So anyway, we think this is pretty important. The other time your molecules changes over time, which we're interpreting as aging. And so our study is a little unique. When people usually study aging, they'll study old people and young people and say, oh, here are the molecules in the old people versus those in the young people, and these are the aging markers. But what's special about us is we're studying the same people so we can see how they're changing over time. And we think you only need as few as 5 measurements to tell how people are aging. And it turns out we're all aging a bit differently. So this one's me with 4 years of data. This is another person, I think it's 3+ years. If you look at me, I'm a pretty typical ager. My molecules and pathways that are changing are coagulation, metabolic, so on and so forth. So I'm a pretty typical ager. This person over here, though, if you look at their top pathway, it's cardiac hypertrophic signaling pathway, meaning they're a cardioager, they're a heart pathway. And we later learned after we published this that they're actually stage 2 hypertensive, which sort of fits with the idea that their cardiovascular system may be a bit stressed. So we've gone on to look at all the people. We had 43 people with enough data to predict what was going on. And we, just like the seasons, we grouped them into patterns. And we call the patterns ageotypes. So this is your aging pattern. And we had 4 major aging types, ageotypes. Now, I know there are more than 4. It's just that that's all we were statistically empowered to say. And so we had kidney, liver, metabolic, immune agers. Okay, so each row is a different ageotype. And I know there's cardioager, but we only had 1 of those, so we weren't statistically empowered to say that. So each column is a different person, each row is an ageotype. And so what we discovered is that there's some people like the 4 down here, they're aging in all 4 categories. This person's aging in 3 of the 4, not much of a kidney ager, but aging these others. I'm somewhere in here, I think this might be me. I'm kidney, liver, and metabolic ager. My immune aging is not too bad, it turns out. And so I actually think that's a good thing. It's good to have a good, robust immune system. This person's a kidney ager. This is kidney and metabolic and so on. So we can tell how people are different, are aging. Not only that, they're actually clinical markers, once again, associated with these ageotypes. And I'll show you a few examples here. And this one's really easy to understand. This is the diabetes marker, hemoglobin A1C. And the group as a whole was going up. That's what this last bar means. It's statistically significant. And if we look at individuals, the dark bar is statistically significant. These 4 people are actually going up in their hemoglobin A1C, which is kind of what you would expect as you get older. But these other 4 people, interestingly enough, are going down. They've reversed their hemoglobin A1C. And in this case, it's pretty easy to see because they had an intervention. So 2 of them went on a diet. 1 exercised, 2 people lost weight. They're overlapping somewhat, as you can see. So that's how they were able to reverse their hemoglobin A1C and to some extent their ageotype. This one's less clear what's going on. This is creatinine, a marker of kidney function. The group as a whole is going up, which is what you would expect. But 10 individuals are statistically significantly going down, and 8 of the 10 are on statins. So it seems as though the statins are actually improving kidney function, at least in these individuals. So we don't fully understand that, can make some possible hypotheses. One of the things we saw, of course, and this we did expect, is that people are aging at different rates. So this is their age in years, and this is their biological age. And so this is using Morgan Levine's, it's called phenoage marker. And what you'll see is there are people whose biological age is greater than their chronological age, meaning they're older than they should be. And these are the folks who are younger than they should be. So that's a good thing. You want to be on this side of the line. And you can see from the slopes of these lines that they're not that accurate because there's a lot of scatter here. But nonetheless, it seems as though some people are definitely aging faster than they should, and others seem to be having slowed down their so-called aging. And so we think this is kind of interesting as well. We can follow people's aging either using other people's markers, but I think the ageotype one is quite valuable because it really can tell you more targeted ways to intervene. So the way we think about all this is that, people are like cars. The whole car does get older, but some parts start wearing out first. So, your transmission or your engine or what have you. And by doing these deep measurements, we can see what parts are going first and take action with the goal of keeping your overall car running fine longer. The goal, of course, for all this is for people to run a real long, healthy lifespan and then health span, I should say, and then basically just die so they don't hang on in some limbo suffering phase there. So that's the goal, keep everybody running happily, okay? Now, one thing I get asked a lot, how are you going to scale this? How are you going to get this out to the world? And I'm in Silicon Valley, so what you do is you form a company. So we formed a company, it's called QBio. Sorry, this is a bit generic. And it's a medical version of what I just showed you. We do more medically validated things, but it's deep data, and they also do whole body MRI. And if you talk to physicians today, virtually every one of them will tell you, do not do a whole body MRI because you're going to find nodules, and it's going to scare people, lead to all kinds of follow-up tests. And my point is that's absolutely wrong. You do want to do whole body MRI, and the issue isn't finding nodules, it's finding growing nodules. And so you need to do it longitudinally. So if you saw any growing nodules, those are the ones you'd go after. And so we all have nodules, by the way. Men have them in their prostate, women in their ovaries, so on and so forth. The question is, are any growing? So anyway, by doing these deep data profiles, MRI and other things, just from the first 100+ people, QBio's found that quite a few, once again, pre-symptomatically discovered some pretty big things: early ovarian cancer, prostate cancer, other things. In most cases, it took multiple kinds of measurements, really tipped off that something was up. And in other cases, it was a longitudinal measurement. So here's a good case: early stage pancreatic cancer, which is almost never caught early stage. Pancreatic cancer is always caught late. And so we caught it early, and that was because we saw this shift in markers occurring over time. So we think this longitudinal profiling for health is a big deal. Lastly, I want to spend some time on our wearable work. Let's see, we're doing fine. So we're very keen on this. We got started on this, I think, about 8.5 years ago, before Apple Watch was out. And we got keen on it because these wearable devices, they were fitness trackers at the time, and people are using them to see how many steps they had, look at their heart rate, and then once they figured out, they threw their watch in the drawer. But we realized these are pretty powerful health monitors. And they're worn in the US by millions of people. Believe it or not, 50 million people wear a smartwatch or smart ring, mostly smartwatches. The reason they're powerful is they take hundreds of thousands of measurements on you each and every day. Some will measure as many as 2.5 million measurements per day. And they track all kinds of different things: heart rate variability, respiration, so on and so forth. Some of them quite accurately, some maybe not as accurately, but you can still see delta shifts. And I should say, I'm a big proponent of these. We use about 8 or 9 every day. So you can see, if you look up, I'm wearing 4 smartwatches right now. I have an environmental sensor. It's a lab thing. Even I recently got hearing aids, believe it or not, and even these will measure certain things. So this is going to be very, very powerful technologies. So anyway, the way we use these is to try and figure out people's baselines and then look for shifts from that. And it turns out, I'll jump right to the chase, we discovered that you could detect infectious disease with a simple smartwatch. And that's what I'm going to tell you about now. And the way we discovered this is when I figured out my Lyme disease, of all things, with a smartwatch and a pulse ox, the thing you put on your finger to measure your blood oxygen. And so, as you can tell, I measure me all the time. And one of the things we found is that on airline flights, people's blood oxygen drops. Well, the backstory I should get into is I was helping my brother put up fences in rural Massachusetts. And then 2 weeks later was flying to Norway. And noticed during the last flight, which was from Frankfurt to Norway, my blood oxygen dropped abnormally low. Now, it normally drops on airlines anyway, but this one dropped especially a median of 90. And then when I landed, it didn't come back to normal compared to all my other measurements on the same kind of flight. Not only that, I noticed that my heart rate was elevated. I later learned my skin temperature is elevated too, and this is plotted at low resolution. So about a day later, after the first noticing this, I actually got symptoms. I ultimately went to a doctor in Norway. I warned him it might be Lyme because of the timing, this 2 weeks. And he basically, pulled blood, said, yep, my monocytes are up. I got a bacterial infection. And he recommended I take penicillin. I said, no, I need doxycycline, which is what you take for Lyme disease. It got a little tense there, but he did give in, which is good. I was about to go above the Arctic Circle, and I didn't want to be ill while that was going on. So anyway, it cleared it up right away. You take it for 2 weeks. When I got back, I got tested, and sure enough, I was Lyme positive by antibody tests, and even had some antigens. And I happened to have given blood 3 days before I left, and I was negative. So it's a really well-controlled experiment. And the bottom line is, again, I actually first detected when I got Lyme disease from a smartwatch and a pulse ox, which is pretty powerful if you think about it. So we went back and looked at the data I had 2 years of data. And during that time, I was sick 4 times. The Lyme time I told you about, this is a viral infection. This we now know is a viral infection. This is the time I was asymptomatic. I had a high C-reactive protein. That's a marker when you're ill. It's just as high as the other times. And every single time I was ill, this is all retrospective, we saw that I had high either resting heart rate, this plot is outlier measurements, you can do it by median values, and I also had high skin temperature. So every time I was ill, including the asymptomatic time, I had elevated resting heart rate and blood temperature. So we wrote an algorithm. It worked well for heart rate, not so much for skin temperature, that can tell when you're getting sick. It's following your baseline, and when you have a significant jump up, it's like a delta plot. You'll see this thing go up, and in every case, again retrospectively, we could show that I had a jump up in heart rate with this algorithm prior to symptoms, and it worked on me all 4 times. It worked on 3 other people, one of whom got sick time. Same thing every time before people got ill. So as you might imagine, when COVID struck, we were improving the algorithm. We published this actually about 5 years ago now. And when COVID struck back in March of 2020, we had been improving the algorithm, building a data infrastructure for doing this. And yeah, it's almost getting ridiculous to show these surges because there's a lot of them. The first ones now seem tiny by comparison. But basically, yeah, we jumped in on this to see if we could actually use this approach to be able to detect COVID and actually build an alerting system. And that's what I'm going to tell you about now. It actually works. We'd like you to sign up for a study. I'll show you the link to sign up. So if you think about the way we're classifying COVID now, the gold standard is PCR, and it's slow. These days, it takes about 2 to 3 days at Stanford. There's so many people getting tested. It's slow. It's kind of costly. And you just can't do it all the time because it's just not convenient for that. There's also these infrared thermometers that work, and they're terrible when the weather's cold outside. Mine always reads about 33 degrees centigrade, which of course, if that were true, I'd probably be dead or pretty close to it. But anyway, the point is these things don't work well at all. And they certainly don't work for SARS very well because the SARS-2 doesn't give much of a fever in many cases. So you totally miss those. So anyway, we wanted to see whether we could detect COVID with a smartwatch. And so that's what I'm going to tell you about. Once the study here, we basically launched an IRB approved study. We kind of had one already. They made us do it for COVID. We partnered with the leading companies, Garmin, Fitbit, what have you. And right away, I enrolled 5,300 people, of which 32 had what we call perfect data sets, in the sense that people were wearing a smartwatch. In this case, Fitbit, we started with. They're wearing a smartwatch. They were basically, they had a COVID diagnosis date and a COVID symptom date. And yeah, and so we could follow what was going on. And this was the very, very first participant we had. This is their diagnosis day. This is their symptom day. And this is their resting heart rate plotted, for those, again, who are aficionados, as a standard deviation plot. And the point out of all this is that you can see this jump up in resting heart rate 9.5 days prior to symptom formation. And I'll tell you about our real-time alerting system in a minute. But bottom line is this person was presumably running around spreading the illness back in March of 2020 without knowing it because they were asymptomatic. And so, yeah, this is why you want to find this stuff early. So it turns out it worked on 26 of 32 participants. It could detect COVID a median of 4 days prior to symptoms, 7 days prior to diagnosis. And it's not specific for COVID. Other illnesses will pick this up as well or get picked up. And so here the median's 2 days prior to symptom onset. And that makes sense because COVID has a longer pre-symptomatic period. And not only that, it's not a huge jump up in signal. The median is 7 beats per minute, but for one individual, it's as little as 2 beats per minute. But it's easy to pick up because you're measuring them. You're making many, many measurements over time. So 2 beats per minute is pretty findable. So we went on to write a real-time detection algorithm. This is still retrospective, but basically purple's diagnosis, red symptoms, and basically what it's doing, it's grabbing your baseline and on an hour-by-hour basis, looking for a jump up in resting heart rate outside of a certain normal value. And if you get enough hours where it jumps up, it will set off this blue, well, ultimately it's a red alarm. I'll show you in a minute. It'll trigger this alarm. And so this individual, I think they're 9 days, this one probably 9 or 7 days. So it does work. It's not, we've set the sensitivity, so it goes off about every 6 weeks on average. And so you do have other bumps. These are real signals. And a lot of people get a bump over the holiday. We know that stress, mental stress, we know that travel, we know that alcohol will all trigger these. 2 drinks for dinner won't do it. But if you really tie one on, you'll probably set off one of these alarms. And again, other illnesses will trigger it. That's one here. There's a healthy person. These are real signals that you see. I don't know what triggered it here. We now know from some of the diagnosis what does it. So we've now gone on to write a real-time alerting system. And it'll send a red signal when we detect this elevation in heart rate. And so here's where you can sign up for a study, innovations.stanford.edu/wearables. We'd love to have all of you sign up because we're trying to improve our algorithms. And we've built now a very lightweight algorithm that's not quite as sensitive, but it's pretty good, but it's scalable. It can work for millions and millions of people. Our goal is to make this for everyone on the planet. There are 3.8 billion people on the planet who have a smartphone. If you compare that with a smartwatch, you'd actually have a health detection system for most of the planet. So anyway, this is just some of the first examples. This is what it looks like. I forgot to sync mine this morning and look at it, but you can see I have this isn't me, this one else had a red alert go off. Their symptoms were then 3 days later, and they were diagnosed here the next day. And it works about 80% of the time. It's not perfect, but it's, it's better than nothing. And yeah, so it's pretty decent. It also works on asymptomatic cases, which is pretty cool. And I should say it works for both Apple Watch and Fitbit pretty equally. And so here's one of the asymptomatic cases. There's a diagnosis day, and you can see all these alarms, all this elevation went off prior to that. Same with this one here, and so on and so forth. So we can pick up asymptomatic cases and even set off these alarms so that what we want you to do is, we know it's a stressor. It doesn't prove it's COVID when you get an alarm, but you can look for it. All right. So I think this is just the tip of the iceberg. Smartwatches, it turns out they read a lot off your wrist. And using machine learning and some of these advanced techniques, we can actually get some level of clinical measurements from a smartwatch, believe it or not. So here's hemoglobin, red blood cell count, hematocrit. You can actually get some level of signal. It's not enough to make a clinical diagnosis. Here's hemoglobin, even diabetes-related measurements, fasting glucose, hemoglobin A1C. So it's not a clinical diagnosis, but if you saw an elevation of this, it'd be enough to trigger something's up that you might, well, is now published. You might go get a follow-up test to see whether this is a real thing or not. And I will say, smartwatches are just one type of sensor. We do a ton with glucose monitoring. I'll just spend a few minutes here, and then we should switch into questions and discussion mode. But basically, we started putting these, they're called continuous glucose monitors. So there's a Dexcom you wear on your hip. You can also wear them on your arm, for Abbott has one. And we started putting these on normal and pre-diabetic. And one of the surprising things we found was that even normal people will be moderate, and some will be severe spikers, much to their surprise. Some people still have good glucose control, but quite a few people are moderate spikers, and there's also a fair number of severe spikers. And so we've written algorithms to be able to classify these excursions, these glucose excursions, and classify people into glucotypes, which is a representation of elevated sugar levels and this excursion. And so there are severe spikers, severe glucotypes, moderate, and low. And so that's how we can measure people with these. One of the things we discovered is that different people spike to different foods. So some people spike to bread and peanut butter, the protein bars. Some people spike to pasta, others to bananas. Everybody's different. Your microbiome's likely responsible for part of that. 80% of people spike to cornflakes and milk. We think this stuff's like poison, possibly should be banned or at least warning labels. Anyway, it's, yeah, so that one's not so good. And once again, we can find people who are severe spikers. They're very, very glucose dysregulated, who actually turned out to be normal by fasting glucose, hemoglobin A1C, even oral glucose tolerance tests. But they got picked up, so they were normal by these standard tests, but they turn out they're severe spikers. So we think these devices can be very, very powerful. And so we've actually formed a company to try and, again, scale this called January AI. So we've now built a system for bringing all the data in the wearable, the clinical, the other data, so you can display it on a screen and actually, show it to the user, whatever resolution they desire, daily, weekly, monthly, what have you. And then the nice thing about wearables, you can actually share it with a physician, so you can basically, do just that. And we think some of the measurements you measure at home are more accurate than what you're going to measure in a physician's office anyway. So this is Mike Snyder's world. I envision a world where people get their genome sequenced before they're born, and then together with these deep biochemical and wearable measurements, physiological measurements, we'll do a better job at predicting disease risk and catching disease early, and also monitor and treat diseases as well. So I'm very fortunate. I have an amazing lab. These are some of the people who in the lab work with it. Slide's getting a little dated here, but when you, Brian, Kevin, Tejas, and others really spearhead a lot of this work. George Weinstock's our wonderful collaborator for the microbiome. Trace McLaughlin, our clinical collaborator. We have a whole wearables team that's shown up here that's been very involved in building the infrastructure, all the smartwatch stuff. Once again, sign up for our study if you have a smartwatch, or if not, you're welcome to buy one and sign up. So innovations.stanford.edu/wearables will take you right to the relevant page. And so that's the story. I think I've left enough time to be able to answer questions from folks. And so let me move into the chat and see what we got here. Wow, there's a lot.
You indeed have left time. We're going to take at least 15 or 20 more minutes to have questions. And we've got a lot, so much we can talk about, but wow, what a tour. Obviously you are just hitting the highest highlights of what you're doing, talking about wearable technologies and characterizing different conditions, aging, diabetes, and you're much more of a splitter than a lumper. You're doing
You can tell that, yes.
So it is personalized medicine. That is sort of the, and let's say personalized health. Let's not get into medicine. We have to. So this is the essence of what you're doing. What do you think are things we can do now and within the next few years with the available technologies we've got? You've already talked about that.
I think the wearables is just going to take right off. I mean, right now you can do this. You can sign up for studies like ours, and it's not perfect, but we'll tell you when you've got a stress event coming, some fraction of which may be due to COVID or other things, and you can do follow-up tests to see what exactly is going on. So I think the wearables is here and now, and you're starting to see companies get into the space. I think it's based in part of the kinds of studies we and others have been running here. So that is front and center. I think the idea about people getting measured more is up there. The biggest problem though right now is who pays.
Right.
So for the average person, so Cube Bio I mentioned, it's $3,500, and you have to pay out of pocket for that. Now, of course, if you have the money, we argue it's worth it because you'll catch things early. Imagine catching one of those cancers early versus waiting till you have symptoms. That's a big deal. But we've really got to shift the health system to pay people to stay healthy. And I think that's the key. Get the employers involved because for them, it's to their benefit if their employees are happy and healthy, get more of these wellness programs. So I just think that's the key. I think there's two things that motivate people. One is money and the other is family. And if we can motivate people using both of those tools, give people rewards on their insurance payments or their healthcare system if they exercise more, eat better, this sort of thing. You need validation measures for this sort of stuff. But I think that's the key. That'll help motivate people. And then maybe that'll trigger an accelerated adoption of some of this stuff. But more frequent measurements is what it's all about, I think, too.
The large cohort you've been following is observational, of course. What about actually doing interventions in a systematic way, even randomized?
Yeah. So get ready. We'll have a paper coming out on fiber consumption. So we had people, it's pretty intense to be one of our studies. They did 3 different fibers. They did the 2 most common, it's called arabinoxylan and inulin. And then they did a mixture and we, they started 10, 20, 30 grams each week, 10 grams first week, 20, second, 30. And then we profile them every week. We draw blood and we draw them after they sort of stop, and we call it the washout phase. So we've been seeing the effects of fiber. It's pretty cool. What we discovered is arabinoxylan, which is pretty common, actually. It's in Physium Hus and things like that, very common. It actually drops people's cholesterol pretty good. I should say at the population level, there's a few people it doesn't work on. It's kind of interesting. So presumably they don't have the right microbiome or something. Inulin, which has been reported to have beneficial effects on glucose, things like that, nope, didn't have any of that for us. So I don't know if it's a different population or what. So this is what we're trying to pin down. I'm a big believer that, food is medicine, and we really need to understand this at the personal level because it really is personalized, these effects. Your microbiome, your genetics, all this weighs in to your response to nutrition. And I think if we could understand that equation, we could solve diabetes.
Yeah, absolutely.
And obesity.
Well, that's a great interest of mine. I'm also very interested in some of your behind the scenes technology. I see, for example, Margareta Colangelo, who's a great expert in AI, and she's taught me something about the coming quantum computing that make AI that much more powerful. What can you tell us a little bit about the technology you're using behind the scenes to parse the data?
Yeah, I mean, we pull the data and we store it. I have 2 petabytes of data just on me, several petabytes of data on the whole cohort. Yeah, and what we're doing is, one is storing it, trying to mine the data to we have correlations with aging and things like that. Where we ultimately hope to go with this is build, personalized profiles. We'll follow people at their individual level and use machine learning to figure out what features are going, steer you a certain direction. If you walk 15 minutes before you eat, maybe you lower your glucose by this much. If you walk 20 minutes or 30 minutes before, maybe you'd steer it down even more. I don't know, and that may turn out to be personalized as well. So we can use machine learning to learn what features correlate with what beneficial health outcomes at all levels, whether it's a glucose readout, whether it's a, heart rate readout, what have you. And actually, it turns out we have some pretty good, January AI has some very good correlations between heart rate and glucose control. So they're building these personalized metabolic control systems as well. So that's really, we think, the name of the game. One is, sure, you can do it at the population level, but I think the future will be at the individual level. And because everybody's different, we want to know how to basically treat you, Zahn, and not, you're going to be different from Mike Snyder and everyone else on this call.
Well, for sure. I related to your comment about fiber and evaluating it, I saw a question about buckwheat. I happen to know something about buckwheat. A Department of Agriculture lab in South Dakota, and buckwheat is healthy. Any further thoughts about dietary interventions that you're exploring or actually studying systematically?
Yeah, well, one is we're expanding now the fibers. Since inulin didn't decrease glucose, we're trying a bunch of other fibers to see what their effects are. And by the way, I should say arabinoxylan taught us, this deep profiling taught us a whole new thing. We saw cholesterol dropped, and the prevailing wisdom is that cholesterol aramidoxyline binds cholesterol and that just physically removes it. But our data actually says, well, actually what it does is from the response, we can tell that bioacids are made, cholesterol is getting broken down. So I don't know if that affects you personally in terms of what you do, but at least we now understand how cholesterol is getting removed by aramidoxyline. It's through metabolism. You're reducing the microbes to actually basically break down cholesterol. So anyway, so we want to test more fibers to see other beneficial effects. We want to try and understand what foods will prevent spikes, right? So that imagine you eat your favorite cupcake, you're going to spike through the roof. I will. I guarantee I hit 300 if I eat a sweet. So I want to understand, well, if I eat, what foods can I eat that will prevent that spike? And that's going to be personalized too, we're finding. So we don't understand it yet. We need to collect more data, but that'll be the goal. So ultimately, you'll do all the things you normally like to do, but you would do them in the right, with the right management system, if that makes sense.
Yeah, well, it does. I'm going to ask my colleague Thomas Sir to come in a second, but just to say we've had a lot of questions about economics, about how medical care could be improved by integrating the intensive data monitoring that you're doing. What's your vision? Do you see that this is going to be mainstream and that the data will feed into the electronic medical record?
I hope so. A lot of people want to keep it personalized and keep it outside the system because they're worried how they'll be adversely affected by it. If you do unveil a bad health condition, maybe your insurance goes up and that sort of thing. So we obviously need protections for that. My pie in the sky would be that you wake up in the morning, you put a finger prick on something that gives you a readout of a bunch of biomarkers, takes another sample that you drop in the FedEx, and 2 days later, you'll get back 1,000 measurements on you. And all the data will show up on your screen in your mirror first thing in the morning. It says, green, 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 green. Uh-oh, orange light on your cholesterol here. Got to go get that followed up. So to be an automated, it's a health dashboard like your car.
Sure.
So you don't drive your car around without a dashboard. And if you've ever had your dashboard light go off, that's a little unsettling. Yet here we are, we're running around with our health with no dashboard, which I find just ridiculous. We should have a dashboard that's like our car dashboard for our health. And people might be scared about it originally, but later you learn, well, just like your car, if you're running low on gas, you want to know that. So that's how I see the system. That would be the Mike Snyder system of the future.
Oh, I love it. Thomas, you've been monitoring the chat. A few questions that you'd like to highlight.
I'm not doing it in order. I'm just sort of going up reverse chron. Jack Mormon asks, you mentioned the idea of being healthy until death. Have there been any studies using wearables, et cetera, for end of life patients?
A good question. Not that I'm aware of. We're being approached a lot now for outpatients trying to measure them, especially people with cardiovascular events. So I think it's coming. And if you think about it, it's a no-brainer. And I like the hearing aid side of this too, because they're often on older folks. And if you could be monitoring them, and the example I used to use a lot was my mom, when she was 9 years old, she would, forget and leave the phone off the hook. And we're 6 of us kids, and somebody would call and they can't get a hold of mom. What's going on? Is there something wrong with mom, or is she okay? And of course, in the end, it's always she left the phone off the hook. So we'd have to call the front desk. She was in this, I don't know, a living area. So somebody had to go over, like, half a mile and come by to check up on her. Whereas if I had a simple smartphone with mom's measurements on there, oh, she's fine. Her heart rate's just fine. It's all good. I don't have to trouble somebody at this location way away. So if you think about it, it's just a no-brainer. And I think parents, with kids would like to know if they're healthy. Hey, look, little Johnny or Janie isn't so great today. They better stay home. You just measure it right on your smartphone. So I just think it could be incorporated right into our living style in a very fruitful fashion.
Pasquale asked, which changes have you noticed in your DNA methylation pattern? You made a reference to it, but didn't really go into it. And which system are you using to get your molecular biological age?
Yeah. So for the methylation part, it was done by whole genome bisulfite. It's one of the most expensive experiments we did. It measured me through the first 4 years of the study when my glucose went off twice. That first time spike, and then later when it went up again, never really came all the way down. And what we discovered was that it's small, it's like just a few percent overall changes in DNA methylation, but it was very focused at the metabolic genes. Very interesting. So our interpretation is that, and you probably know that methylation affects gene expression, usually shuts it off. In this case, some went off, some went low, some went high, more low. And so what happened was, more methylation went high, gene expression went low. So our interpretation is that even though it's a rather modest effect, it's over hundreds of metabolic genes, and that's enough to bugger up my glucose. And that's our interpretation of this. And so I think it's going to be a lot of fun to see if that happens with COVID.
Johnny Adams, this is a sort of a commercial question. I wanted to ask you more about your service. I'm interested in signing up your study and looking into your service. But Johnny Adams asked, do you have any experience with the Oura ring? I'm wearing a hoop myself, but apparently they've raised some money. So I don't know if this is competitive compared to your other startups, but any general observations on the actual companies that are commercializing stuff out there?
Sure. Yeah, so everybody's running these studies now to detect COVID. We just happen to be pretty well positioned because we had been working in this area already. So the Oura ring is, I think, really nice. It takes most of its measurements at night, which is fine. It detects sleep duration really, really well. But by the way, I think sleep is a biggie. Getting back to Zan's point, that's one we were trying to incorporate into our studies to understand the biological effects of sleep in many different forms. So anyway, the Oura ring, I think they're all going to work for disease detection. What the right resolution is, things like this, I think is going to be powerful. Now, Apple Watches and Fitbits, they're all-purpose devices. They actually turn down the resolution during the day because they're trying to save battery. And we think, from a health monitoring, that's not so good. So here's where I'm 100% conflict, but we build a watch Sensomics that's more optimized for health. And I think the Whoop is intended to be that way as well. I just haven't had time to evaluate Whoop. So anyway, what we've found is, that high resolution when people are resting is a pretty good way to pick up health problems. So that's one reason I wear 4 of these things, so I can actually tell, we're trying to figure out what the optimal resolution is for different kinds of conditions, whether it's an infectious disease or mental stress or what have you, see what we can learn from these different devices and different kinds of measurements tease out, not surprisingly, different things. I'm quite confident at the end, I know we can tell the difference between a bacterial and a viral infection. I'm pretty sure we'll be able to tell, we can't right now, the difference between mental stress and a viral infection. It's hard to get the data. It's another reason we formed our own company. You can't get the raw data from any of these companies. They hoard it. So that is a problem. And so I know that if we can get respiration, all these things from a smartwatch, we'll do much, much better. I don't know if we'll ever be able to tell the difference, for example, between influenza and COVID. We just have to see.
And back to your company, did you call it QBio? Is it? You said 3,500 for a first workup, or is it what is it on a maintenance basis, and how can?
It's 3,500 every visit. Yeah, and we don't know, but we're recommending 2 visits a year, right? We don't know what the right number is. I don't think anybody does.
Can you envision the future where you could democratize that? As you said, you could get gross level of resolution with smartphones and algorithms and so forth, but
get ready. Get ready. They'll be they have some pretty powerful technology that will drive this out there. I think first of all, the blood test stuff will become Amazonized, if that's a word. It's just a no-brainer to me, right? Every other sector behaves that way. The big equipment, which is still going to be important and powerful, we're gonna that is not going to be advertised. You can't mail those things around.
MRI,
yeah. So I think, but there's no reason not to have them in CVSs and places like that, where people, just like you're getting, 30 years ago, who thought about getting vaccinated at a CVS? Well, now everybody can get vaccinated at CVS or in a parking lot even. So I think we can set this up and get it out there. And the ultimate goal is to get it down to a few $100s. But that's the way these new technologies work, as I'm sure you appreciate for anyone who's a startup person here. They're expensive when they begin. You have to get the technology all up and working. You have to, and to be honest, set up the system and recoup your costs. And then as you scale it and get bigger and bigger, hopefully the costs will drop. That's the hope anyway. I'm pretty sure that'll be true for QBio and these other companies that I've been involved with.
Zan, we're at the 1:15 mark. Do you want to close the formal period? I don't know how much longer we have Michael with us, but we could open it up to a salon or after session for people who want to speak up if they have follow-on questions or other questions, additional questions.
Mike, do you have 5 or 10 minutes more to?
Yeah, why don't I hang on? I forgot to check what my next appointment was. That leaves you guys in a pretty good spot.
So less data is good in some circumstances. Okay, good.
Well,
I'm looking at it. It's not a problem to borrow more time. So let's happy to keep going.
yeah, well, let's talk about geroscience and the
Okay,
world
sure.
trying to do something about the aging process. You've mentioned diabetes in general as kind of an accelerated aging process, but that's
Absolutely, yeah.
gross simplification. Do you see a distinction between slowing the aging process and the prospects of actually reversing aging from a mechanistic standpoint? I mean, you're a geneticist. You look at the omics of it. Do you see some means of studying that distinction between just the progressive loss of function and some way of gaining function, and how we study that with your platform?
Yeah. So the answer is actually, well, let me back up. I follow this field pretty closely, believe it or not, maybe because I'm getting older, but it's also because I'm hanging out with these friends who are total, they're biohackers and they really want to control their health span. And so one of them is a VC and he's investing in all these longevity companies. So I'm a believer you should be able to reverse aging. And exactly how, I don't know. I know the one way to slow aging is keep your immune system boosted. I think that's the number one thing. I think that's why exercise and eating healthy works. Turmeric and these things, they're immune system boosters. And they, you may or may not know, you're getting cancer your whole life and your immune system just clears it. And once you hit your 60s, your ability to recognize diverse molecules and things plummets. And that's why I think COVID has problems, things like that. So we need to keep our immune system boosted so that we can clear and boost in a way where it's still recognizing diverse foreign particles, and whether it be cancer or things that, these genetic changes that occur in you, or whether it's foreign other things. So that's the number one thing. So I'm pretty keen on that, technologies that do that sort of thing. I think if you want to reverse aging, there's a lot of interest in senolytics, getting rid of senescent cells. I think that's a fascinating area, and certainly could have the promise to actually, minimally maintain your age, but possibly reverse it too if you can stimulate stem cell growth and things like that. The tricky part about stimulating stem cell growth is you don't want to be causing cancer, so there's that right balance. And all these folks who do like human growth hormone, people who claim they can actually reverse aging and boost your immune system. They say, we do that and has no effect on cancer. I don't think they really know for the long term because cancer doesn't just come up in a year or two. It takes 10, 20 years.
Although maybe with your metrics, you can predict that sooner, but okay.
Well, that's the hope. Or maybe what you do is if you do something like that, you make sure you have suicide genes of a cell goes off. You can actually wipe it out with a kind of marker that's sitting there. So there could be some interesting ideas, but I'm a believer that we will control our health span and ideally reverse. I'm pretty sure we'll be able to reverse our lifespan. The question is, will it be done fast enough so people like me can take advantage of it? And maybe some of the others on this call. I'm a pretty strong believer. People are born, first of all, it's pretty much stated now, anybody born now will live to be 100 for the most part. And then for, I would think anybody in the first who's less than 20 may live forever, because we should be able to control those cells. So yeah, I think it's about, but what you don't want to do, you got to keep your brain functioning. So if you're going to keep because you do lose, what's 50,000 neurons a day, but you got to replace those, or at least some new connections. So we do need to keep our stem cells, keeping healthy parts of our body for all parts of our body. But I do think the age type work we're doing is powerful, because minimally, if you see your heart is having problem, like that stage 2 hypertensive person, that should have been a red flag that we should have caught that, told them before. We got the data in late. They found they were stage 2 hypertensive after we told them their age type. In the future, I want to tell them look, something's off with your cardiovascular system here while you're still healthy, and you're heading in a wrong trajectory. We have had cases, by the way. We had one person's liver marker was the bottom of the normal range, and suddenly it jumped to the high end of normal. And of course, nobody's saying anything because it's still normal. And then, of course, the next measurement was just outside the norm. We said, something's up with that person. He's got liver problems. And so they adjusted and actually got it right back to normal. But again, very, very early. And that's the way the world's got to work. And it's got to be automated too.
Mike, let's take maybe 3 questions from our audience. Anybody who wants to pipe up, show yourself and ask a question. I see Jack Moorman there. If you want to ask a question, Jack, go right ahead.
Yeah, Mike, I'm, of course, a big fan of yours and the recent article in Stanford Magazine. So this baseline that you've mentioned, QBio is obviously one way. Is there an alternative to such an expensive thing to begin, a baseline?
Well, the smartwatch, I think it's a pretty simple way to start. So definitely, all right, good. Fitbit, I see it. Yeah, by all means, feel free. And by the way, we have a lot of studies running. The Wearables is a pretty easy one. We have some CGM ones and some others are remote. If you're in the Bay Area, you can do the more intensive ones I described, like the fiber and stuff. So not sure where all you folks are. Some of you were not even on this continent, I saw. I think that's the easiest way to get started. The problem is none of the stuff is FDA approved and all these sorts of things. But if I were you, I would be, checking on my hemoglobin A1C. You can buy those things at Walgreens. I forgot what it is, $40, $50 for 2 tests. There are things you can buy that you probably want to keep an eye on. Now, there are also studies where you can do, I think glucose monitoring is a biggie, by the way, because you may know 9% of the US is diabetic and 33% is pre-diabetic, and 70% of those pre-diabetics will become diabetic. I actually think the diabetes endemic is worse than the COVID pandemic, if you think about it. And they're not unrelated, since one can lead to the other. But so I think glucose monitoring is a no-brainer. There are a couple of companies doing it. I mentioned mine, January AI, that actually not only does monitoring, but it's actually it has behavioral interventions as well. It's meant to teach you what foods will spike you, recommend those that don't, you like this, that spikes you, try this one, which is similar but healthier for you. We have beautiful, it's called GLGI database, glycemic index. So those things I think are going to get out there right away. Wearables and glucose monitoring. In Europe, they're over the counter. In the US, you still need a physician. So or go through one of these companies, which involves physicians. What else is out there? I think just getting more monitoring in general and that stuff, we need more home devices. And so we're working on that sort of thing.
Do you use a ketone meter?
Yeah, I've seen it. We haven't done it. Love to do it. Yeah, I'm very interested in this because I have very little carbs. So I'm very interested in ketosis and things for what I'm eating. So, and exercise routine. So yeah, would be a good
My
one.
keto blower.
Yeah.
Well, Mike, this has been amazing. We could go on and on, but I know you've got to get on to your next demand. Thomas, why don't you close this out? But Mike, just again, many, many thanks. You have been terrific.
Oh, well, thank you.
There are going to be a lot more people looking at the recording when it's available, and certainly
Okay.
we're going to.
Yeah, reach out with questions, by the way. If we don't get to yours, I haven't looked at all the ones in the chat, but I'm happy to answer questions offline. So, but let's do the last one you mentioned there. Was that Tom? Did you say?
Yeah, go ahead, Thomas.
Oh, the close. Well, the last question or the close? Because there's a question here. Sorry, last minute. We're trying to squeeze every last ounce out of you, Michael.
Go for it.
What are you doing in the microbiome? I know that you made a reference to that, but that seems to be pretty significant. I know you're looking at nutrition and so forth, but how would you comment on where you are?
Yeah, so I mentioned how different people are reacting to different fibers. I'm sure the microbiome is part of it. Microbiome is interesting. Everybody knows it's important, yet there's no clinically actionable information from it yet. Yet. It will be there. Nobody's quite made that connection. We all know it's valuable. So what we're doing, I think what we're going to find is that if microbiome, not by itself, but with other markers, is going to predict how you react to what fibers you should eat and such. And that's what I predict will be the future, because we all have some of a good microbiome in there already, but maybe not enough of some other things. And so I think that measurement, along with others, will be very, very predictive of your response to foods. And that will be the future. And you just do the test, periodically, and boom, it'll tell you this is what you should eat. Maybe it'll even load you up with a few probiotics.
Even beyond food, but the microbiome ties to the brain-gut axis in response to infections, etc.
Totally.
Really opening my eyes to, depression.
Yeah, depression, autism has been linked to the microbiome. Yeah, so I think it will play into a role. Good point there, Thomas. Yeah, sorry to cut you off. Yeah.
Well, listen, it is approaching 1:30 on the East Coast. I want to thank everybody. The terrific questions from the audience. Fascinating presentation, Mike. Again, this webcast will be posted to our Kitalys website, and by early next week, all of you will get notices, so you can listen again, or tell people who might have missed the presentation. We welcome feedback, raves, or constructive suggestions, topics you'd like to see us cover in the future. You can reach us by the contact us functionality at kitalys.org. So with that, with thanks to everybody, we wish you a great day.
And thanks again, Mike.
Okay, thank you.
Terrific.
Bye all.
Thanks. Bye-bye.
Well and prosper.